Picture a scenario that plays out in tech companies literally every single day. You're evaluating this massive, state-of-the-art machine learning model for deployment.
Right, a classic scenario.
Exactly. You're running rigorous A/B tests, calculating all these complex variances, and your pipeline confidently outputs a p-value saying your new model is a statistically significant improvement.
So you push it to production.
You push it to production.
Yeah.
But over the next few weeks, performance degrades. The lift just wasn't real.
Yeah, that is the worst feeling.
It really is. You start digging into your pipeline, obsessing over your data quality, your resampling methods, your code.
But what if I told you the problem wasn't your code at all?
Wait, really? Then what is it?
What if it was a mathematical approximation embedded in statistical software that was derived 80 years ago? A foundation that we've known for decades fundamentally cracks under very specific, highly common modern resampling conditions.
It's a genuinely unsettling realization for anyone working in inference. You have this towering structure of modeling complexity resting on a localized structural vulnerability that honestly most practitioners just assume is ground truth.
Oh, absolutely. We just trust the libraries we import.
Right. And for those of you listening, the data scientists, the machine learning engineers, the mathematicians building today's complex modeling and survey pipelines, that vulnerability is Satterthwaite's approximation for effective degrees of freedom.
Like a true classic.
Yeah. Today, the mission of this deep dive is to dissect a 2024 paper by Matthias von Davier titled A Modified Satterthwaite Effective Degrees of Freedom Approximation.
Which is such a crucial paper.
It really is. We're looking at a foundational equation from 1941 and 1946. We use Satterthwaite constantly to calculate confidence intervals for complex variance estimators. But it fundamentally breaks down when your component degrees of freedom are small.
Yeah, and what stands out as truly remarkable about von Davier's 2024 paper is the pure theoretical approach to the fix.
Right, because we've had fixes before, haven't we?
Exactly. I mean, for over 30 years, the statistical community has essentially relied on an empirical, simulation-based Band-Aid to patch those cracks in Satterthwaite's logic.
Just a Band-Aid.
Yeah, but von Davier strips all of that heuristic patchwork away. He doesn't rely on simulations or hard-coded constants.
Oh, wow.
He grounds his correction purely in analytical results regarding the higher moments of standard, normal, random variables. He solves a modern computational problem with rigorous, classical mathematical proofs.
A generalized theoretical solution instead of a localized heuristic is exactly what we want to see. But to truly appreciate the elegance of von Davier's correction, we first need to establish exactly where and why the original classical approximation fails in our modern environments.
Good idea. Let's set the stage.
So let's set the stage with Satterthwaite. The setup is something most of us have encountered in our day-to-day work. We have a complex estimate of variance, which is just the sum of independent variance estimates across several different components.
Right, and the ultimate goal in that scenario is to approximate the distribution of this complex sum as a chi-square distribution.
Because that makes everything easier.
Right, exactly. By doing that, we can easily calculate p-values or confidence intervals. But to map our complex variance to a chi-square distribution, we absolutely must find its unknown effective degrees of freedom.
Okay, let's unpack this. The classical Satterthwaite formula tells us to do this by matching the moments.
Right.
We take the variance of the complex estimate, and we set it equal to the variance of our target chi-square distribution. But to make the algebra resolve, Satterthwaite does something a bit dangerous.
Very dangerous in certain contexts.
Yeah, he essentially replaces the true unknown population variances with the sample variance estimates. Now, as data scientists, we know plug-in estimators can be incredibly risky.
Oh, for sure.
You can't always just swap a population parameter for a sample statistic and expect the expected values to behave perfectly. Why exactly does this specific plug-in assumption break down so badly?
Well, the breakdown stems from a very specific assumption Satterthwaite explicitly made back in the 1940s. He assumed that the degrees of freedom for each individual variance component were at least moderate in size.
Moderate size.
Yeah. Think about the behavior of a sample variance physically. When your degrees of freedom are large, your sample variance is a highly reliable, tightly concentrated estimate of the true population variance.
Right, because you have enough data. The variance of the variance itself is small.
Exactly. But when your degrees of freedom are very small, that sample estimate becomes highly volatile. And when you plug a highly volatile estimate into a nonlinear equation, The mathematical expectations completely unravel.
And that unraveling happens most spectacularly at the absolute minimum boundary, right? When the component degrees of freedom equal exactly 1.
Yes, that is the danger zone.
And I want to emphasize to you listening that this isn't just some rare theoretical edge case. In modern data science, we hit a degree of freedom of 1 all the time.
Oh, constantly.
If you're using jackknife resampling to estimate variance in complex survey designs, you are essentially leaving one observation out at a time. That means each pseudo-value you generate only contributes a single degree of freedom to the component estimate.
Jackknife is a perfect example, as is balanced repeated replicates, or BRR. In those ubiquitous resampling scenarios, Satterthwaite's approximation becomes highly unstable.
Because of that volatility.
Right. Because the sample variance is so volatile at a degree of freedom of 1, the approximation systematically and severely underestimates the true effective degrees of freedom of the complex sum.
Which is a huge problem.
It is. The downstream effect is that you end up with confidence intervals that are wildly overly conservative, simply because the formula assumes a level of precision in the variance components that simply does not exist.
So let me summarize where we are. We have a foundational mathematical formula from 1946 that systematically fails, producing overly conservative bounds under the exact resampling conditions that we rely on today.
This raises an important question. How did the statistical community deal with this glaring failure for the last 3 decades?
Right, because we certainly didn't abandon jackknife or BRR in our pipelines.
Far from it. We leaned into them as computing power grew.
And this brings us to the empirical Band-Aid of 1992. When I was going through this part of the source material, I honestly couldn't help but cringe.
Yeah, it's a bit painful for a mathematician to read.
It really is. It felt identical to what happens when a machine learning model is failing in production, producing out-of-bounds predictions, and a frustrated engineer just hard-codes a multiplier to force the outputs back into a reasonable range.
That is a highly accurate description of what occurred, actually. In 1992, Eugene Johnson and Keith Rust were working on the National Assessment of Educational Progress, commonly known as NAEP.
The big education survey.
Right. They recognized that Satterthwaite was significantly underestimating the true degrees of freedom for their jackknife-based variance estimates, where, as we discussed, the degrees of freedom equal 1.
So what did they do?
Well, rather than deriving a new theoretical model, they ran a massive simulation study to figure out exactly how far off Satterthwaite's approximation was on average.
I see. So their solution was to derive an empirical adjustment multiplier.
Exactly, a heuristic.
They proposed a correction factor that involves subtracting a fraction based on the square root of the number of components from a constant. You multiply the Satterthwaite estimate by this heuristic factor, and suddenly your degrees of freedom look correct again.
Well, they look correct for that very specific use case. It is a pure heuristic.
Right.
The adjustment wasn't derived from the fundamental properties of the normal or chi-square distributions involved. It was entirely reverse-engineered from the results of their localized simulations.
It's the statistical equivalent of overfitting a hyperparameter to a single training set.
Exactly.
The Johnson and Rust formula works beautifully for NAEP.
Right.
In their specific survey design, the number of primary sampling units, the components, was exactly 62. And because they used jackknife, the component degrees of freedom was 1. If you plug those exact parameters into their heuristic multiplier, you get an adjustment of roughly 2.8.
Which works for them.
Yeah, for that highly specific configuration, multiplying the result by 2.8 effectively patches the crack in Satterthwaite's foundation.
But any data scientist intuitively knows that an overfit heuristic generalizes poorly to unseen data.
Terribly.
The von Davier paper provides a phenomenal breakdown of this failure in Table 1 of the source material. He maps out the relationship between the number of components, the component degrees of freedom, and the median ratio of Satterthwaite's approximation using that 1992 NAEP adjustment compared to the true degrees of freedom.
I'm looking at those numbers now, and they are damning. The adjustment does its job when the degrees of freedom equal 1.
Yes.
But look what happens when you try to use that same multiplier for generalized statistical software, where your survey design or resampling pipeline might have a much larger number of components or larger component degrees of freedom.
The divergence becomes completely unacceptable for generalized inference. Let's trace the data.
Okay.
Imagine you have a pipeline with 100 components, and the degrees of freedom for each component is 25.
Which is pretty standard.
Right. Under those specific conditions, the original Satterthwaite approximation is actually quite accurate on its own because 25 is a moderate number. The volatility of the sample variance has stabilized.
Okay, that makes sense.
But if your statistical software blindly applies the NAEP adjustment to it, the ratio of the estimated degrees of freedom to the true degrees of freedom balloons to 2.681.
Wait, 2.681. Let me translate that into real-world impact. That means the adjusted formula claims you have over 2.5 times the degrees of freedom that you actually possess.
Exactly. It's a massive overestimation.
You'd be reporting a massive level of statistical confidence, generating tiny p-values that are entirely phantom. You'd be pushing models to production based on noise.
It creates a massive risk of false positives. And despite this glaring generalization problem, this simulation-based workaround has been hard-coded into assessment program software and various statistical libraries for decades.
That's terrifying.
It is. The community recognized a desperate need for a rigorous mathematical solution that works across the entire parameter space rather than relying on a fragile patch.
Here's where it gets really interesting. Matthias von Davier provides that exact solution.
He does.
Having established the failure of both the original approximation at low samples and the 1992 empirical workaround at high samples, we can finally dive into von Davier's analytical breakthrough. And it starts by locating the exact mathematical flaw in Satterthwaite's original plug-in logic.
To understand the fundamental flaw, we have to look at the expected value of squared variances.
Right.
When Satterthwaite mathematically derives the effective degrees of freedom, the final formula requires dividing a term by the square of the true unknown population variance. Since the true variance is unknown, Satterthwaite simply plugs in the sample variance squared.
Which, on the surface, seems completely intuitive. If a sample variance is an unbiased estimator of a population variance, then squaring the sample variance should give you the population variance squared.
This sounds right.
Yeah, but von Davier points out that this assumes the expected value of a squared sample variance is equivalent to the squared population variance. And for small degrees of freedom, this is demonstrably mathematically false.
It all comes down to the behavior of the higher moments of normal random variables.
Let's break that down.
Von Davier walks through the critical analytical identities in the paper, and it hinges on how variance itself inflates expectations. We know that a sample variance, appropriately scaled by its degrees of freedom, follows a chi-square distribution.
And a chi-square random variable is fundamentally just the sum of squared standard normal random variables.
Precisely. Now, we need the expected value of the square of that chi-square variable. Von Davier utilizes a fundamental statistical identity that we often overlook. The expected value of any squared random variable is not simply the square of its mean. It is the square of its mean plus its variance.
Okay, let me pause you there, because that is the crux of the entire issue.
It really is.
If you square a random variable, the volatility, the variance of that variable, directly inflates the expected value. For our chi-square variable, the mean is equal to the degrees of freedom, let's call it nu, and the variance is 2 times nu.
Right. Applying that fundamental identity, the expected value of the squared chi-square variable is its mean squared, which is nu squared, plus its variance, which is 2 nu.
So nu squared plus 2 nu.
Exactly. If you factor out the nu, the expectation becomes nu multiplied by the quantity of nu plus 2.
Oh, wow. I see the trap now. When you translate that mathematical reality back from the chi-square scale to the scale of our everyday sample variances, you find that the expected value of your squared sample variance is heavily inflated.
Very heavily inflated.
It is not simply the true squared variance. It is inflated by a factor of the degrees of freedom plus 2, divided by the degrees of freedom.
That inflation factor is the hidden killer in Satterthwaite's approximation. Let's look at the physical mechanics of it.
Okay.
If your degrees of freedom is a large number, say 100, then 102 divided by 100 is 1.02. It's basically 1. Satterthwaite's original assumption essentially holds true.
Because the variance of the sample of the variance is so small, it doesn't inflate the expectation.
Right. But if your degrees of freedom is 1, like in Jackknife resampling, then 1 plus 2 is 3 divided by 1 is 3.
Wait, 3?
Yes. The expected value of your squared sample variance is 3 times larger than the true squared variance you are actually trying to estimate.
That's huge.
Yeah.
Just by squaring the sample estimate, you have introduced a massive systematic bias.
Therefore, the theoretically correct plug-in replacement requires adjusting the denominator in Satterthwaite's original formula. Satterthwaite originally divided a term by the degrees of freedom, nu.
Right.
Von Davier proves that to cancel out that massive expectation inflation, we must instead divide by nu plus 2.
Oh, that's brilliant.
By making that simple, analytically derived substitution, von Davier perfectly aligns the mathematical expectations for the individual variance components, regardless of how incredibly small the degrees of freedom might be.
It's incredibly elegant. There are no simulations, no arbitrary multipliers tuned to a specific survey design. He's just tracking the actual mathematical expectations of the higher moment and correcting for the inherent variance of the estimators.
It's pure math.
But von Davier's paper doesn't stop at the denominator, right?
No, and what's fascinating here is von Davier recognizes that fixing the individual variance components in the denominator is only half the structural repair.
Okay, what's the other half?
Well, Satterthwaite's formula also relies on substituting the square of the complex variance, the total sum, with the square of the sum of the sample variances in the numerator.
Oh, right.
And the act of squaring that entire complex sum introduces a very similar expectation inflation that also requires correction when you have a small number of components and small component degrees of freedom.
That makes intuitive sense. If you only have, say, two variance components that you're summing together, the expectation of that squared sum is going to be highly volatile and subject to the exact same inflation dynamic we just explored.
Exactly. Von Davier meticulously proves that to make the expected value of the squared complex variance estimate track correctly to its population target, you need a specific numerator correction multiplier.
A new multiplier.
Yeah, he denotes this derived multiplier as lambda star.
Let's describe the shape of that multiplier without getting bogged down in the raw notation. For the common scenario where all your variance components share the exact same degrees of freedom, von Davier derives a lambda star that is essentially 1 plus a fraction.
Right.
And the denominator of that fraction scales based on the number of components and the degrees of freedom.
It perfectly complements the denominator adjustment. This allows von Davier to finally construct a generalized estimator that theoretically holds under any condition.
So he puts it all together.
Yes. Bringing these mathematically derived identities together, he presents his final effective degrees of freedom estimator, labeled as equation 3 in the source text.
Conceptually, the new estimator takes the core structure of Satterthwaite, but it applies von Davier's nu plus 2 correction to the denominator, and it multiplies the numerator by that dynamically scaling lambda star correction factor.
It represents a profound modernization of the original 1946 methodology. But as any mathematician will tell you, the true test of a generalized estimator is how it behaves at the extreme boundaries of its parameter space.
We need to test the theoretical limits of equation 3. Let's test the absolute minimums first.
Let's do it.
Imagine an environment where you only have two components, and each has a degree of freedom of 1. This isn't theoretical. This is the exact scenario you face when utilizing Welch's t-test for comparing two means with unequal variances, or in Rubin Schenker's classic approach to evaluating multiple imputations.
Under those absolute minimum conditions, if you evaluate von Davier's lambda star multiplier, the fraction maximizes. The multiplier peaks at exactly 3.
Wait, exactly 3?
Yes, it peaks exactly where the expected value inflation of the squared variance is mathematically at its most severe. It provides the maximum necessary mathematical adjustment to prevent the equation from underestimating the degrees of freedom.
That handles the lower bounds perfectly. What about the opposite extreme, the asymptotic limits? As data scientists dealing with massive data sets, we absolutely need to know that as our sample size is scaled to infinity, our underlying mathematical equations don't destabilize or overcorrect.
The asymptotic behavior is where the true beauty of an analytical derivation shines compared to a heuristic.
How so?
Consider what happens to von Davier's adjustments as the number of components approaches infinity, or as the individual degrees of freedom approach infinity. Look at that lambda star adjustment term.
The 1 plus a fraction 1.
Right, because it is 1 plus a fraction where the parameters are in the denominator. As those parameters grow infinitely large, the fraction approaches 0.
Oh, I see. The adjustment term perfectly and smoothly approaches 1. It effectively turns itself off when it's no longer needed.
Exactly. And the exact same mathematical vanishing act happens with the nu plus 2 correction in the denominator.
Let me guess. As the degrees of freedom grows toward infinity, adding 2 becomes mathematically irrelevant.
You got it. The terms seamlessly cancel out, meaning this new von Davier estimator naturally collapses back into the classical, unadjusted Satterthwaite equation for large samples. It bridges the gap perfectly.
So what does this all mean? We have a theoretically derived equation that dominates at small sample sizes, by correcting for expectation inflation and smoothly collapses to the classical foundation at large sample sizes.
Which is exactly what you want.
Right. But theory is just theory. How does it actually perform against the data?
We can validate it by looking directly at Table 2 in von Davier's paper. Think back to how the Johnson and Rust empirical heuristic from NAEP wildly overestimated the degrees of freedom when the parameters grew.
Oh, I remember it well. At 100 components and a degree of freedom of 25, the NAEP adjustment yielded an unacceptable ratio of 2.681.
In Table 2, von Davier runs his new theoretical estimator against those exact same parameters. At that extreme case of 100 components and 25 degrees of freedom, the ratio of von Davier's estimated degrees of freedom to the true target degrees of freedom is 1.004.
Wow. That is virtually perfect.
It flawlessly tracks the true degrees of freedom across all parameter values mapped in the table, from the notoriously difficult bounds of a single degree of freedom all the way up to 25.
Amazing.
It completely removes the downward bias that plagued Satterthwaite for small values without triggering the disastrous overadjustments of the 1992 heuristic for large values.
It is an incredible piece of rigorous scholarship. To summarize the core of this deep dive, Matthias von Davier successfully replaced a 30-year-old empirical simulation heuristic with a rigorous classical mathematical proof.
A huge step forward.
Yeah, by accurately accounting for the expected values of the higher moments of normal distributions, specifically recognizing that the variance of a sample variance heavily inflates its expected value when squared. He created a truly generalized effective degrees of freedom estimator.
One that works universally.
Exactly. Scaling flawlessly from the constraints of jackknife free sampling environments all the way up to infinite degrees of freedom.
If we connect this to the bigger picture, understanding this paper is far more than just a satisfying academic exercise in mathematical theory.
Oh, definitely.
This specific formula dictates the variance estimates, the standard errors, and ultimately the confidence intervals in vast survey analyses, automated assessment programs, and modern ML resampling pipelines.
It's everywhere.
It dictates the boundaries of statistical significance across countless domains. By replacing a brittle, overfit empirical constant with a theoretically sound analytical adjustment, von Davier has fundamentally reinforced the foundation of our statistical inference.
Which leaves you with a final thought to mull over. As you go back to your own modeling pipelines, think about the massive open source machine learning and statistical libraries you import and use every single day.
The ones we just take for granted.
Right. The functions you call without a second thought. How many other standard constants or empirical band-aids are quietly hiding in those legacy code bases? Code that was originally reverse engineered from a localized simulation in the 90s, just waiting for someone to derive the rigorous, analytical, mathematical truth beneath them.
It makes you wonder.
It really does. The mathematical foundations of your most advanced models might be older and significantly more fragile than you think.